I'll be talking to you more about mechanical and electrical engineering and how it relates to FTC. Also, I've been on 1313-2 minor blue for 6 years. Last year was my last year, so thank you. The most important thing that you're going to find in starting out in FTC with getting your first challenge and designing your first robot is research. To pick a good drivetrain, to pick a good design for your overall robot, you need to do your research. Because most likely, ideas that you come up with have already been done previously. If you're a new team, you're going to want to reach out to another team near you. Hopefully they respond, and most likely they'll be able to help you out. Make sure to put your research in your notebook. This is very important because my team, I know, would always forget the research that they did and try to backtrack and wouldn't get it done. So there are also lots of kits and lots of part suppliers you can go for. They all have different kits. I don't really have a specific recommendation. Go Build the kits are, I think, the most popular kit, but the top 4 that you see there are the most popular kits in general. These are also the part suppliers that you can buy from. Andy Mark, Amazon, Servo City, so forth and so on. Highly recommend, if you have a phone, take a picture of that slide, because if you look for any parts later on for FTC, you'll definitely want to be looking at those suppliers to buy from. So this is a very simple setup for a drivetrain. You have a slim battery. It doesn't necessarily have to be a slim battery. It could be a thicker battery, which runs that power to the control hub or an expansion hub. If you have an expansion hub, usually as the name states, you're usually expanding on that control hub so that you can wire in other motors, other servos, other sensors. The ports on the bottom of the hub are generally used for sensors. The ports on the side of the hub are generally used for bigger HD and hex motors. So, yes. Any questions so far? So, identifying motors on 2 of the chassis that my team prototyped last year. The motors you can't very well see, they're down here. In this case, they're hiding in the C channel. There are multiple different designs that you can use to incorporate the motors in your drivetrain. In this case, this is a direct drive motor, so there are no gears in between the motor and the wheels. In this other case, there are gears running against each other, allowing that motor to be rotated and turned into the C channel without being direct drive. There are multiple different chassis designs that you can go with. These are just a couple to give you a baseline. Tank drive, holonomic, swerve, I'll get to all of those in a second. These are a couple different designs that I've seen personally at different competitions. I really like that triangle design. I found that very cool. My team was prototyping a octagon design for our robot, so that didn't really come to fruition, but just to give you an idea, really try to step out of the box and come up with really crazy designs. It is possible to have the designs work. They might be complicated, but never think anything's impossible. So generally a tank drive design, you're going to have like 3 wheels on each side of the robot, running right next to each other. In the case of possibly going over any barriers or any other objects, a tank drive design would be ideal for that. It does have its setbacks though. In any case, you can generally get stuck on things as well. So every drivetrain has its ups and downs. The Holonama drivetrain allows you to move in multiple different orientations. I find this very cool. My team generally uses this. It's very crazy to see how these wheels allow you to strafe sideways. So not only can your robot move back and forward and rotate around, but it can also go side to side and can pretty move at any axis other than up and down. Swerve train designs are very interesting because they allow you to orient your robot at any given axis at like anything, other than up and down, of course. But I have personally never had any experience with these. I find the idea very interesting, and I have seen quite a few at competition, but they are quite complicated and require quite a few parts. So these are all the different wheel designs. I am a very huge fan of the 3D printed design. If you have access to a 3D printer, I highly recommend looking into that a little bit more. The one thing that needs to be noted is if you put any sort of tread on the wheels, most likely if you spin your motors too fast, the wheels will tear up the foam tiles and you'll get a penalty or you'll be disqualified. These are a couple of the different designs that my team has used in the past with pincer grips, roller grips, and finger-like grips. This is an entirely 3D printed claw. We also have a gear, and this works off of a servo, which is that smaller motor. Doesn't require as much power. This also works off of a servo. We were intentionally trying to make the design as lightweight as possible, which is why we first tried to 3D print it. Then we made a different kind of model. And the benefit here and the difference between this one and that one, the pincer claws close on one certain point. So imagine you're going with your fingers and you're going like that. The pincer claws only close at that one point right there. With this claw, it's essentially going like this, compared to closing at one given point. So, and then the roller design was made to intake a cone-shaped object. It's very interesting to see how it works. You can put pretty much any type of servo in any given side and rotate the wheels upward and intake possibly a block or a orb or whatever you might want to do, just depending on how far you space the wheels out. Things to note and other things, invest in reliability. Usually parts are pretty expensive, so you have to note that. Generally, if you spend a little bit more money, you'll get usually you'll get a higher quality part. Other problems that my team encountered, and I know other teams encountered at competition, watch out for static electricity. My team personally didn't experience this, but I know some other teams did. There are different types of static sprays that you might be able to use to mitigate that issue. Set screws are also another common issue. If you have any set screws in any sort of wheel configuration where that set screw is going against an axle and a motor and it's being constantly spun one direction or the other, it's very possible that that set screw will come loose. And generally in Tetrix parts, the metal is made soft. Unfortunately, that's just a problem that Tetrix parts have. We found a good fix for this was using McMaster-Carr set screws, and they have a higher build quality, and generally they're a higher grade metal. Designs and features. I actually don't have, I learned a little bit about this as well. Plexiglass is alright. It's generally a little bit cheaper. You can see on the 1352 robot there, the side panels are made out of plexiglass. We've had issues in the past where those plexiglass pieces will break off. Usually if you use Lexan, you don't have to worry about that. It's a little bit more flexible, and you won't have to worry about it bending too much and breaking or shattering or cracking. And for Lexan, you can use it for different applications. You can use it for bumpers on the side of the robot. But with plexiglass, if you ram the wall too hard by accident or on purpose, you'll have a very good chance of breaking those bumpers on your robot. The other good option for bumpers on your robot is to 3D print something that you can use as a bumper. Always remember, greatest professionalism, thanks to Dean Kamen. This is going to be brought up many times in your FTC season. If you haven't already been in FTC, the KISS method, keep it simple, stupid. Every single time, every single year, my team has forgotten about this. It is very important to remember that method, because it's way too easy to make something way too complicated, and as soon as you make it complicated, first off, if it ever breaks, it's complicated to take it apart. And if anything goes wrong, it's complicated to take it apart. It's always complicated. So remember that. Thanks for listening. If you have any questions, email me, or if you have any questions now. So thanks for listening. Currently, I'm hoping to go to S&T for my mechanical engineering degree. I've started one college course, and I've found a hobby in restoring cars of many different vintages, from the 1950s all the way back to the 1920s. I have an internship at Rolla, and yes.
Could you show some of the various things you've included on your robot design?
Yeah, sure.
Well, last year's robot design, I suppose.
So, one of the different things is, first off, we had a slide to pick up our claw, and essentially using this slide, we were able to lift up different objects. This was our beacon for last year. I don't know who all was in an FTC team or on an FTC team. But this is one of many different designs that we went through. Essentially, the way this claw works is there's a worm gear inside the C channel here. It spins 2 gears on each side, and then spins these gears, which are all connected, which spins the 2 wheels and then picks up different objects. And then, like how I was talking about with the gears being kind of strangely situated, instead of going as a direct drive system, and I'll turn this around here, we have it going to 2 gears, and that allows us to spin that motor and have it connected to those wheels. Okay, any more questions? Even if it's about the robot or personal questions? Okay, thank you for listening.
Okay.